This video is meant to be an easy demonstration of the loop rule and the junction rule for DC circuits. The junction rule is basically a statement of conservation of charge. To check that, you would use an ammeter. The loop rule is related to conservation of energy, and to verify that, you would use a voltmeter. I'm going to start with the loop rule, so I'm going to take this multimeter and set it up as a voltmeter. So I'm going to turn the rotary knob not to AC volts, but DC volts. Plug one banana plug cable into the common plug. We just call it that because we always use it for every measurement. And then the other one I'm going to plug in to the volts plug. So I've got one red cable and one black cable. And now if I'm just kind of handling the wires, you can see that the readings fluctuate quite a bit. That's because I don't really have a complete circuit, and a voltmeter needs to be in contact with a complete circuit in order to measure anything. In this kind of situation, we say that the connectors are, the probes are floating. If I connect the two banana plug connectors together like this, now I've shorted across the two inputs, and I get 0, which I should, because the voltage difference between any 2 points on a conductor should be 0 in a DC circuit. Now to check that my voltmeter is actually working, I've got this 3-volt camera battery that I had around. I'm going to put the black on the negative terminal of the battery and the red probe on the other end, and I get about the right voltage. And notice how it's reading positive. That's because what it's telling me right now is the difference in voltage between the red and the black. If I turn the battery around, now it's reading -3. This kind of thing can be pretty confusing to watch somebody else do as they're making all the connections to the meter and taking data. So I'm going to start off with a fake mock-up of my loop rule. So here I'm using the gravitational metaphor for an electric circuit where height is the same as voltage. So if this was a circuit, we could say that here's the battery where I'm raising you up. I'm going to say it's 5 inches from there to there. Then you come over here and you drop down 3 inches down those books. And then that's a resistor, and then you drop down another 2 inches down this book, that's another resistor, and you come back to the start. And then there are actually 2 ways that you could verify the loop rule. One way would be like this. I'm going to keep it so that I've always got a consistent handedness around this loop. So here I've got the red counterclockwise from the black, and I can measure this. And since I'm measuring a height difference, red minus black, I'm going to get 5 inches, or 5 volts. Then if I keep on going around the circuit, always keeping the red counterclockwise from the black, that would read -3, because the red height minus the black height is -3. And then -2. And the sum of those 3 voltages would be 0. That's one way of expressing the loop rule. Often in a circuit, you know which direction is downhill, and sometimes then it's easier to work only with positive quantities. So if I was going to do that style of loop rule for this circuit, what I would do is this. I would go like this. I would measure red minus black height, which is 5, positive 5. Then to verify that, I would do the other side of the loop. I would here get +3, and here I would get +2, excuse me. So with this style, all of the numbers are positive by definition, and also kind of because I was able to anticipate which direction was down. So then that is the same as that without having to worry about signs. And another thing I could do is I can just kind of imagine rotating the circuit around like this. And if I think about it that way, then my two probes just kind of go like this, and I keep on making and breaking contact over here. Okay, now I'm going to check the loop rule for an actual circuit. So I've got my 3-volt camera battery again. This is a resistor, and this is another resistor with a different value over here. First I'm going to measure across the battery, and notice how I have the red wire on the counterclockwise side, and it reads 3.056 with a positive sign, 3.056 volts. Then I'm going to just rotate the whole circuit this way. I still have the same consistent handedness for the probes. And now I'm getting negative 2.781 volts. Keep on spinning the whole circuit around. And now I'm getting negative 0.275 volts. So if you need to write down those numbers, you can stop the video at those points, pause it, and write those down. Now I'm going to demonstrate the same thing, showing the other way of handling the signs, where we just make sure that we treat every number as positive. Here, this is the side of the battery with the positive nipple, so I know that's sort of the uphill end of the hill. So if this was a roller coaster, I would be going up, and then down, and then down. So I'm just going to intentionally always put the red probe at the uphill end of everything, and all my numbers will come out to be positive height differences. So if I do it that way, I get 3.055 volts with a positive sign. Over here, I'm still going to keep the red at the uphill end, and I get positive 2.781 volts. And again, over here, keeping the red at the uphill end, I get positive 0.274 volts. So now, just like with the books, this height difference, which is positive, just equals this height difference plus this height difference. Now let's test the junction rule. So this circuit may be a little harder to see. I've got a power supply right here. The red wire is connected to the positive side of the voltage supply. Comes to here. Here's a resistor, which is very small. Then we have a junction right there. Keep that junction in mind, because that's the one we're going to use to test the junction rule. Coming out of the other side of the junction, we have a blue wire and a yellow wire. The blue wire comes to another of these small resistors that goes from there to there. The yellow wire comes here to another small resistor that goes from there to there. And then from this junction, current flows back through the black wire to the negative side of the power supply. To make it clearer what that is, in case you're having trouble seeing that, that's the circuit right there. This junction is the one that I've picked that I'm going to use to test the junction rule. The other three-way junction in the circuit is that, but I'm just picking this one to test. So to test the junction rule with that junction, I need to measure a current here, here, and here, at those three places. So to measure current with an ammeter, you have to break the circuit apart, for instance at a spot like that, insert the meter like a toll booth that the electric charge is forced to flow through, and then after you're done, close up that gap and do the next measurement. Now I'm going to set up my meter to measure current. So I put it on one of the current scales, which can read in units of amps or milliamps. So that would be the one I would use for fairly big currents. And if you notice up here on the screen, it says AAC. That means AC amps. We don't want AC. This is a DC circuit. On this particular meter, the way you switch it is that you have to look at these two icons. There's a white sine wave icon for AC, and then the yellow dot dash icon for DC. The yellow is telling you to push this yellow button over here. Now it says amps DC. So now I need to measure these currents that I've labeled current 1, current 2, and current 3. Just like with the loop rule, there's an issue with how you handle the signs, and there's more than one way to do it. The way I'm going to do it here is I kind of know which way all of these currents are going to go. I know that current in all three of these resistors is going to flow to the right. Therefore, I'm going to hook up the meter always with the red plug on the left, so that current will always be flowing in the red plug of the meter and out through the black plug of the meter. And then I'm going to expect that this number would equal this number plus this number. Now as I'm getting ready to test the junction rule at this junction right here, I have my wires plugged in. For the red one, I had a choice. I don't know if you can see these labels very well, they're pretty small. I had a choice of either an amps plug or a milliamp and microamps plug. I'm anticipating that my currents will probably be in the milliamp range, I'm not really sure. So I put it in the milliamps plug, and I'm on a milliamp scale, and the meter says milliamps DC. So now I'm going to go ahead and measure that current that I was calling current 1, which is the current coming in through this resistor right here. To do that, anytime I want to use an ammeter, it has to be in series. That means I have to break the circuit. I could break the circuit by opening up that alligator clip right there, but it's probably easier just to pull the banana plug out of the tail end of that alligator clip. Like that. So now I've broken the circuit. I'm going to connect that end to the red plug in the meter. And this end to the black amps plug. I planned that out so that I would get a positive reading showing current flowing to the right. So the meter reads positive when current goes in its amps plug and out of its common plug. Now that I see the reading, I can see that I'm only getting 2 sig figs, which is not that great. So I'm going to switch to a more sensitive scale in order to get more precision. So I'm going to switch to the milliamps scale. This meter has a really annoying habit of then immediately switching me to AC, which isn't what I wanted. So I'm going to push the yellow button again, put it back on DC. So now I get that reading in microamps with 4 sig figs of precision, which is a big win. So it's 458.8 microamps. Now that I'm done taking that reading, I have to repair the break I made in the circuit. So there's my circuit back the way it was before. Now I'm going to measure the current in this blue branch of the circuit. Again, the easy place to break it is here, where the banana plug cable goes in. Again, connecting so that currents that flow to the right are positive. And I get 41.1 microamps. So very little of the current is going off through that blue branch. Taking my meter back out, putting the circuit back together. I'm once again back to my original circuit. Now I want to measure the current going through this yellow branch. So it's clear now that the bulk of the current was flowing through that yellow branch. That must be a much smaller resistor. And here I have 414.6 microamps.